Mhm. Okay. Thanks for inviting me here, and thanks for coming to my talk. So, this is based on the paper that I wrote in the end of last year, and also something that is in preparation with Arash and Dongming at the moment. So, the idea of this talk is to use four-dimensional n equals 2 superconformal field theories reduced on the cigar with some kind of topological twist as a device that's unifying several constructions that's been studied over the past roughly decade. The constructions being one is the SCFT VOA correspondence, where this Beamer-Stelli and others kind of business where you construct fine vertex algebra inside the four-dimensional superconformal field theory. Another being the boundary VOA in 3D n equals 4 theories, the construction of Gayotta-Costello. And then there are also vertex algebras in the context of 2D 0,2 theories, and the recent developments on three-dimensional n equals 4 SCFT of so-called rank 0 theories that were introduced by Masahito and Dongming. So let's start. I will start with a 4D n equals 2 SCFT on the cigar. So what do I mean by this? Let's put 4D n equals 2 superconformal field theory on the product of a cigar with some kind of topological twist and the Riemann surface. Well, when the Riemann surface is non-trivial, it's going to support a holomorphic twist. So it's going to be holomorphic topological twist that's available in 4D n equals 2 theories and sometimes referred to as Kapustian twist. But oftentimes, sigma can be thought as just flat complex plane, so just a holomorphic direction, whereas this one is the topological direction. And because it's topological, you can shrink it to take the limit where it becomes a half line, and in this case, you generate some canonical boundary condition at the endpoint of this half line. So what kind of twist am I going to use on C? So, I mean, there are several options. I could try to twist it by the U1 capital R, the Cartan subalgebra of SU2 R symmetry. This would lead to so this okay here I would call this the 3D limit, because here you literally get some three-dimensional theory with boundary conditions. So if I use this twist by U1 capital R, I would get some 2,2 boundary condition. This twist looks like a 2D A twist on this cigar. It also follows from the four-dimensional Donaldson-Witten twist, and it leads to the story of Nekrasov-Witten. But this is not the one. I'm just mentioning it for review purposes. I'm more interested in the other twist, which is, as I mentioned before, this HT or Kapustian twist in this context, where you use U1 little r symmetry that is only available in T's. So I'm assuming that four-dimensional theory is superconformal. And this leads to a 0,4 boundary condition here that I call H. So this boundary condition H. From the point of view of C, this looks like a B twist. The U1 little r looks like an axial R symmetry, from the point of view of two-dimensional theory on C. And more precisely, I'm actually interested not just by this twist, but this twist and omega deformation along C. So C will be always assumed to have a U1 isometry. So this if you look at it from the point of C, it looks like an omega deformed B model. And this is the setup that gives sort of this alternative definition of the chiral algebra of Beam and others, where instead of using the Q plus S supercharge, you use this omega background. This was done by Yagi O and also by Subyak Jong 5 years ago. So, as I said, this approach is like an alternative approach to formulating this SCFT VOA correspondence. And one of the points is that it localizes, like this theory localizes to, by supersymmetric localization, to the vertex operator algebra on sigma, and this is precisely the Beam and others VOA. For example, in Lagrangian, this can be made quite explicit in the Lagrangian case. So just, for example, if we have a Lagrangian four-dimensional theory with gauge group G and representation of hypermultiplets, which is R plus var, as usual, then this theory can be formulated as a 2D 2,2 theory on C with infinitely many fields, where the gauge group is some sort of maps from sigma to G, and we have a pair of chiral multiplets, and they're chirals. Let's call them gamma and beta. Gamma is valued in maps from sigma to G, and then I can also multiply it, say, by the square root of the canonical bundle on sigma. Beta is also maps from, not G, representation R. And beta maps from sigma to the dual representation, again, this. And this theory also has a superpotential, so which is beta del bar of this type. And so it's a 2D 2,2 model, but with this sort of in fields, infinite many fields, where the target space is like the space of maps, and the corresponding B model supercharge, it's known to admit the omega deformation, and then it localizes roughly it localizes to like a 2D theory with the action beta del bar gamma, or in other words, gauged beta gamma system. So it's the known answer for in the abelian case, in the Lagrangian case, but then by sort of abstract reasoning, we expect that the same construction goes through in all cases. It's just that we don't have such an explicit description in non-Lagrangian examples. The omega deformation, so just the amount of how I. Now let me remind you a few important points that are actually were also important in the Nekrasov-Witten story. So what I'm running the part of this story is actually just sort of repeating Nekrasov's Witten story, but in the case of this B twist on C. So first point is that omega deformation of this 2D theory is non-trivial on R2, in the sense that it's a non-trivial deformation of the theory, since let's say the rotation of the plane it does not appear. It's not part of the. It does not appear on the right-hand side of Q squared in the Poincare algebra, in the super Poincare algebra. So since it does not appear in Q squared of super Poincare, so in order to get something like this, one indeed needs a non-trivial deformation on R2. However, it is trivial. This deformation becomes trivial on the cylinder. So if we are on the cylinder, so locally it's just like flat space, but then we have this direction phi, and we consider deformation with respect to rotation of the cylinder. But this rotation of the cylinder locally, it's just translation. And translations do appear in like when you take squares of Poincare supercharges. And correspondingly, there exists a field redefinition that removes omega deformation on the cylinder. So in other words, IE is removable by a field redefinition. Now, however, if we consider the cigar, maybe let me continue here. On cigar, there's some flat region here. So, and in the flat region, like locally, it looks just like the cylinder. So omega deformation is removable here by a field redefinition, whereas in the curved region, it cannot be removed, so it's actually non-trivial here. So what does it mean? It means that as we take the 3D limit, which, as I said previously, means that I shrink the cigar and turn it into a half line, what I get in the presence of omega deformation, I get, again, a half line where this flat region is the same, gives me the same 3D theory that I had before. So here I get some 3D n equals 4 bulk. But the boundary condition that originates from this tip of the cigar, it gets deformed. And I'm going to call the deformed boundary condition H epsilon. So this H epsilon is some epsilon deformation of the origin of the 0,4 boundary condition H in this 3D n equals 4 theory, the boundary condition that I get just by reducing on the topologically twisted cigar. Now, the important point is that I will make is that this deformed boundary condition, just like H, it is importantly, it is a holomorphic boundary condition. It is a which is compatible with a 3D topological, what's sometimes called A twist, or sometimes it's called H twist. So I can apply this topological twist in the bulk, and the boundary condition turns out to be still compatible with it and becomes a holomorphic boundary condition. So what is this boundary condition, and what is the deformation? By doing what? Yes. 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 Well, at least in the Lagrangian case, absolutely. There is one subtlety which plays a role in non-Lagrangian examples, that you have this topological twist. So there is a unit flux of our symmetry, which creates a unit monodromy of U1R. It's irrelevant in the Lagrangian case, but I will talk about this in the second half of the talk. So what is this deformation? Well, it turns out that H epsilon can be thought of as starting with so a 3D bulk. We have H, the undeformed boundary condition, and then we add some kind of boundary interaction, boundary deformation, which is epsilon times integral over, well, let's call boundary. I mean, it's sigma, the same sigma, of some operator O. In Lagrangian example, one can, the one that I mentioned before, and one can just run this procedure and explicitly compute the O, and turns out to be proportional to the complex conjugate of the superpotential, this superpotential. Now, more generally, what is this O? Well, the answer is that it's the what I would call it Castello-Gaiota deformation. Of the 0,4 boundary condition. Let me briefly explain what this deformation is. Now, if we have a 0,4 boundary condition, I will denote the supercharges that are preserved by such a boundary condition, small q plus bar, and then q plus prime, and q plus prime bar. So there are 4 supercharges. These two form 0,2 algebra, and these two form 0,2 algebra. Now, if I have 2,2 boundary condition, the supercharges would be, let's say, q plus bar, which is the same as these two. Then there are supercharges of opposite chirality, q minus and q minus bar. And The supercharge that's identified with this topological A twist or H twist, let me call it Q3DA, it's actually Q bar plus Q minus. And I'm free to put some parameter here in front of Q minus because I can, by complexified R symmetry transformations, I can always make this parameter arbitrary non-zero number. So we see that the topological supercharge is compatible with 2,2 boundary conditions, but not with the 0,4 boundary conditions. And in fact, 2,2 boundary conditions, in the topologically twisted theory, they lead to topological boundary conditions. So 2,2, first of all, they're compatible, so they're okay, preserved, and they give topological boundary conditions in this 3D TQFT that's obtained by the 3D A twist. Let's call it TQFT A. Now 0,4 are not compatible. So, but if you take 0,4 boundary condition, for example, our boundary condition H, that's engineered by the cigar. What we can do, it's not compatible, right? Not compatible with QA3D. Oh, it was whatever 3DA. So the way to fix this is to add the boundary interaction. Maybe like this. Such that it is invariant under Q plus and Q minus, and under Q plus bar, it gives a component of the supersymmetry current that is normal to the boundary. So this is a SUSY current for Q minus. So one can check that in the presence of such a boundary deformation, that's what this Castello-Gayotto deformation is, you get that the Q bar plus epsilon Q minus, this 3DA charge, and also in addition Q plus, they are preserved. And boundary condition H with this deformation, that's what we call it H epsilon. So this H epsilon boundary condition preserves at least these two supercharges, and you see that they actually form a sort of 0,2 supersymmetry algebra, these two supercharges. And so at the level of cohomology of the topological supercharge, the boundary condition is holomorphic. So meaning that, well, it's the standard story where you take cohomology of this supercharge, the anti-commutator of this and this gives you anti-holomorphic translations. So at the level of cohomology, you only have holomorphic objects. And one comment also that these kind of relations where you connect supersymmetry currents to other things by supersymmetry, they appear, of course, in the stress energy tensor multiplet. And one can check that 3D superconformal stress tensor multiplet implies or suggests that we can take the component of the R-symmetry current. Let me go like this. So here JH is the SU2H R-symmetry current. This is the R-symmetry in 3D n equals 4, and it's the same one as SU2R that I called SU2R in the 4-dimensional theory, right? And this is a holomorphic component along the boundary. So that's like the general choice of the boundary deformation. And you can also check that the answer that I gave here, that it's the complex conjugate of this of the superpotential, is actually agrees with this. So this is equal to W bar in Lagrangian examples, in Lagrangian case. All right, so there's this boundary deformation. And so the conclusion here is that basically that the omega deformation of 4D HT, or homomorphic topological twist, where C is taken to be a cigar, this thing in the 3D limit becomes the Costello-Gayotta deformation of 0,4 boundary condition H, compatible with 3D topological A or H twist. Okay, so and in case you were wondering, this is a remark, what is this boundary condition H? H is, in a sense, can be thought of as a 0,4 version of like some kind of space filling brane. In other words, Neumann boundary condition. So okay, so this story so far, it links the 4D SCFT VOA correspondence to this boundary VOAs in 3D n equals 4 theories. And well, since there's it's compatible with the topological twist, let's perform the topological twist in 3D. So after 3D A or H twist, we have the following configuration. So there's a boundary H epsilon, which is a holomorphic boundary condition. In case we obtain our theory from 4D SCFT, now it's, well, I mean, that's the case that we consider here. It supports VOA V, which is the same as beam at VOA in 4D. And then in 3D bulk, we have a 3D TQFT A, which is, well, in this precise setting, it's a non-unitary. By topological twist, you get non-unitary VOAs. Let me list some general properties of this setup. So so yeah, yes. Of course, for a very particular choice of boundary condition. Also, yeah. Well, then it's not the same. Then it's not the same theory, right? You need to have precisely the one that you obtain from 4 dimensions. Yeah, yeah. So general facts, perhaps. First, um, when you have lines, so line operators, or you can call them anyons, in this TQFT A, they lead to modules of the VOA. In an obvious way, if you have a line, you can end it at your boundary, and it's gonna generate you a VOA module. Um, uh, it's expected to be equivalence with the right choice of category of V modules, which, of course, in the rational case is obvious what's the category. In outside of rational case, it's always a struggle to identify the correct category. And it's going to be sometimes it's going to be a modular tensor category. A spoiler alert is that happens if 3D theory is rank 0. Well, at least in those cases. Then, of course, if we have sort of point number 1.5, because it's almost trivially follows from this, is that when we have 2,2 surface operators in 4 dimensions, you can wrap them on C, and they again lead to lines, so topological lines in this TQFT A, and again modules. But the fact that surface operators in 4D give you modules of the B modal VOA, it's been known. Now another general thing is that point number 2 sort of states, if you have consider states in this TQFT in the Hilbert space associated to sigma, so states in this TQFT A are, of course, conformal blocks for VOAV, in the sense that, like, you have your sigma, you have some bulk, you have some insertions O1, On along the boundary that belong to the boundary VOA. There's some state incoming here, and this configuration computes you sort of correlation, boundary correlation functions. You can call it in-state psi, which are precisely what gives you a conformal block. Closely related configuration is putting this theory on the slab, where you have the holomorphic boundary condition H epsilon on the left, and topological boundary condition B that originates from some 2,2 boundary condition in the theory before the twist. On the right, so after you collide the two boundaries, you get some 2D effective description. 2D effective theory, let me call it TB epsilon. Now, it turns out that somehow the presence of this second boundary kills the deformation, and this TB epsilon, like in the strict 2D limit where you collide the boundaries, it's the same as T0, TB0, so there's no deformation. So we just have a 0,4 boundary condition on the left, 2,2 on the right, and this is some, so it's just some two-dimensional 0,2 theory that you obtain after the interval reduction. These two-dimensional theories also going to have some chiral algebra, like the one in the cohomology of the supercharge. So this T0b has chiral algebra, let me call it V hat, which is extension of V. It contains V, but it's in general extension because there can be line operators that connect the two boundaries. And so in the 2D limit, they extend V. And then you can similarly consider 2D chiral correlators in this two-dimensional theory. Let me call it like this, which again give you conformal blocks for V, well, which this is related to the previous case because you can, of course, consider the boundary state associated to this boundary. Right. And another general point that I wanted to make is that Schur index of your 4D SCFT after all this manipulation, yes. Well, for both, but yeah. Here I want to make more point is for V, but also for V hat, of course. Now, the Schur index of your four-dimensional SCFT after this manipulations in terms of the 3D theory is actually, it's a solid torus partition function. Right. Where at the boundary of the solid torus, you impose boundary condition H epsilon. This actually suggests that this construction perhaps can be used to prove Cordova-Shao formula of for the Schur index in terms of Kontsevich-Soibel monodromy. But yes. Say again. Yes. No, it's gonna be the no epsilon depends in the Schur index, and Q in the Schur index it's actually it's gonna be the, let me see, I think it's the complex structure of this torus. It's yeah. McDonald's index, you said? I'm not sure. I haven't thought about this, but maybe. Uh, I mean, certainly you can refine by flavor holonomics, but that's trivial. Oh, that's precisely what Cyril was saying. Yeah, both for both. Yeah. Hmm. Yes, yes. The solely torus partition function is like a half index of the boundary condition. Half index is the character that counts the boundary operators in the VOA, in the boundary VOA. But here in this construction, by definition, the boundary VOA, like its vacuum module, is the same VOA that you get in 4 dimensions, which is why the half index of this boundary condition counts the sure character, the vacuum module, right? Okay. Yeah, it should be some. It should be like there should be some way to do it like this, because it's like you have an interval with. So there's one circle that you don't touch, and then there are 2 circles that shrink on one end of the interval or the other end of the interval. Yeah. Um, yeah, it's a little confusing. Well, yeah, well, because then there you would have to like you reduce. Here you also get non-compact from compact when you reduce in the cigar, because you get the effective boundary from the tip of the cigar. So it's should be something like that here as well. But you don't really need to do that to make this statement. This is just sort of automatic, because this partition function counts the character of the boundary VOA, and you know that the vacuum character. The vacuum character is the Schur index. Yes, yes, and here it means here you would have to insert line operators in the center of this solid torus. Okay, now let me go to next part. I don't remember if I was keeping the count, but it's part 5, whatever. And Xeon twisted reductions. So what I mean. So as I was saying earlier, answering to Cyril's question, when here when you have a topological twist, it's really supported in the curved region of your cigar. So it means that here in the curved region, you have a flux unit flux of U1R symmetry, or rather, it means that like there's the corresponding gauge field for this R symmetry, and here we have a unit flux. Well, the presence of this unit flux means that here we get a sort of unit holonomy of U1R. Now, of course, this is identity, but what it really means, that if you have some operator or some field phi of U1R charge R, then this field acquires a monodromy e to the 2 pi I r as you go around the circle. Well, it depends on how you normalize the. I use a normalization where supercharges have r charge 1/2 for little r, so then it's unit. Now, if r is not integer, if it's in particular it's a fractional number, then this field is not periodic along the circle. It acquires some phase as you go around the circle. Now, if all our charges have a common denominator n, then we get a Zn twisted, sort of Zn twisted reduction, circle reduction. Of the 4D theory. Now, this Zn here is actually a global symmetry that such theories have. So this Zn is a discrete, is a global symmetry of such theories. This observation goes back, I guess, to my paper with Gukov, Nakajima, Dupé, who's here, and yeah, and in fact, this global symmetry sort of extends the naive choice of U1 little r, so you can write it in the form of the following short exact sequence. Let's think of Zn additively, it's convenient for whatever purposes, but then the rest are multiplicative. So the choice of, so if I have this unit holonomy around the circle, it's 1 mod n here, and it maps to the nth root of unity, the primitive nth root of unity like this, which is then mapped to just identity. So this is like the naive choice of our symmetry, and this is the n-sheeted covering that exists in theories with fractional R charges, and this plays Zn, it commutes with supersymmetry and plays the role of like discrete flavor symmetry. So when we do this circle reduction, it is well known in the case when gamma is 0. So gamma equals 0 circle reduction. Is well known, but then here we have this sort of gamma equals 1, or we can even turn on other values of gamma. And they are very different, actually, in general. Now, for Lagrangian theories, they happen to be the same because in these conventions, all the fields in the Lagrangian theory have fractional little r, integer little r, therefore nothing happens. But in non-Lagrangian theories, they are different. So when we have gamma non-zero, it lifts or partially lifts, in particular gamma equals 1, partially lifts the Coulomb branch. Oh. In fact, when the four-dimensional theory obeys the sort of non-integrality condition that, which was like the observation made here, that when all the coordinates on your Coulomb branch have fractional R charges, this is the non-integrality condition, then the Coulomb branch is completely lifted. So R non-integrality implies that Coulomb branch is fully lifted in the three-dimensional limit. Now, sometimes we know that sometimes four-dimensional theories also have no Higgs branch. If 4D theory has no Higgs branch, then we get in 3 dimensions a theory without a Coulomb or Higgs branch. So then we get rank 0 theory in 3 dimensions. A good family of examples of this sort are Algebras theories of type A k minus 1, A n minus 1, where the greatest common divisor of k and n is 1. So these theories have no Higgs branch, and they also obey non-integrality. In fact, there are quite a lot of Algebras theories obey non-integrality, but they may also have Higgs branches. So these ones have none. In this case, by the way, each of these theories has a Zn, this type of global symmetry with n equal to, should I, let me call this M. So they have Zn global symmetry with n equal to k plus m. So a twisted reduction of such theories is going to lead to some family of rank 0 theories labeled by k and m. Which well, certainly at the time when it was written, this family was not known, but there was a lot of papers in this field appearing in the last couple of weeks. Maybe by now this family is already known, I'm not sure. But certainly when there's a conjecture that the family of Algebras theories of type A1, A2n, in which case you take, again, reduction with gamma equals 1 in this group Z 2n plus 3. They, after the reduction, they lead to 3D n equals 4 rank 0 theories Tn, which were, like this particular family was constructed in Gang Kim Stabs. So these are some 3D n equals 2 Chern-Simons matter theories that exhibit SUSY enhancement to n equals 4 and so on. And in particular, one of them, T1, also known as the minimal 3D n equals 4 SCFT, it's the minimal rank 0 theory of Dongmin and Masahito. Well, evidence for this conjecture is that here the chiral algebra is the minimal model. So here VOA is the 2n plus 3 minimal model. And in these theories, you get characters of the same minimal model as half indices and so on. Now, this can be in the remaining time, let me quickly go through one example, which is actually the subject of this paper in preparation, namely the A1, A2. So A1, A2 case. If you consider gamma equals 1, and in this case, by the way, the group is Z5, this discrete symmetry. So we consider reduction with gamma equals 1, mod 5. And look at the reduction, study the index. Actually, so a reduction of S1 cross S3b score sphere, the background that computes you a superconformal index. So gamma is holonomy here along this circle. And so what is this reduction? Is the high temperature limit, right? High temperature limit, but because of this discrete holonomy, this is limit on the second sheet. Note, however, that this is not the same second sheet that people studied in the context of the black hole counting, where you consider similar second sheet, but with respect to the 4D n equals 1 R symmetry. Here, it's a different second sheet. In particular, there's no temperatures, like 1 over beta squared term in the exponential starts with 1 over beta for whatever reason. But you can study this high temperature limit. Now the index, it's of course it has some matrix model representation, it's some contour integral of some expression, which the details are not relevant, but this expression is written using n equals 1, 4D n equals 1 Lagrangian descriptions. So Lagrangian for A1, A2, the ones due to Maruyoshi and Song. And then what one does is the saddle point approximation in this integral. You sort of identify the right saddle point that contributes in the high temperature limit, and then zoom in and sort of turn the contour integral into the just a fine integral that computes you the sphere partition function. So doing this saddle point in this integral star you get matrix model. Well, in this case, it's not really matrix. There's only one variable, but in general, it's still referred to as matrix model. Computing partition function of this three-dimensional theory on S3, and including the dependence of the squashing parameter. And now you have the integral, you look at the integrand, and you can read off the 3D theory. It's going to be a 3D n equals 2 theory, because I started with a 4D n equals 1. And what is this theory? Well, in the case of this reduction with gamma equals 1, this leads to the theory which is U1 with Chern-Simons level 3/2 plus charge 1 chiral, let's call it phi 1. This theory has SUSY enhancement to n equals 4, and that's precisely the description of this minimal rank 0 theory. So this is the Gang Yamazaki theory. So you perform this Z5 twisted reduction of A1, A2, sort of the minimal 4D n equals 2 SCFT, and you get the minimal rank 0 theory in 3D n equals 4. On the other hand, if I perform this, and I'm almost done. I'm like, I know. Yeah. If you perform the same reduction now on the third sheet, and on the third sheet means that I take gamma equals 2 mod 5. Here, the similar saddle point analysis in the holonomy Z seems to lead to the theory, which is it starts the same. It's U1 level 3/2 plus charge 1 chiral phi 1, and plus there's a charge minus 2 chiral phi. And then, sort of from like naturalness arguments, you can include superpotential with the possible relevant terms like phi 1 squared, phi minus 2, and one of the monopoles, actually the monopole of charge minus 1, also has the right quantum numbers to be included in the superpotential. And this theory it actually gapped. It's a gapped. And being gapped, it just flows to a unitary TQFT. Whereas in this case, if I take this theory and perform its topological twist, I get the Li-Yang TQFT, which is non-unitary. Wait. Sorry, say again? Oh. They are both generators of Z5, that's true. Therefore, it applies that they both completely lift the Coulomb branch, and so it's consistent, but there's no contradiction a priori. It's like just maybe surprising slightly. By computing what? I mean, twisted partition. What do you mean by twisted? Twisted index, you mean? Sure. Yeah, well, so if you, yeah, uh, no. If you have a 3D TQFT, you can compute it on different um, manifolds and use that partition function to extract the SNT matrices. So um, here, like if you have this theory, you topologically twist it, and then you might ask, how do I extract the SNT matrices? And then I would have precisely do that, just compute various partition functions, or compute handle gluing operators and fibering operators, and they would give me matrix elements of SNT. Yes, that's right. And then by doing this reduction with different values of gamma, you get this other theories like this one. So here in this case, sort of the final map roadmap is like this. When I have gamma equals 1, I get this rank 0 theory, rank 0 SCFT, and then by doing the 3D the topological A twist, it gives me a Li-Yang TQFT, the one whose MTC is it corresponds to the minimal model M, the non-unitary minimal model M25. On the other hand, if I do gamma equals 2, I get actually gapped theory, which then which automatically flows to a TQFT. And in fact, this TQFT can be identified as the um, whatever, like some fermionized tricriticalizing model, which happens to be the same as a supersymmetric minimum n equals 1 supersymmetric minimal model 3.5. Tensor a free Majorana fermion. Um, Whatever, this one has central charge 7/11th, no 7/10th, and then like this one is 1/2, and then um, together they combine to the central charge 6/5. So what somehow this 6/5 is also the same as the, so here's a cute interesting observation. So this is the same as the central charge of Fibonacci TQFT. And if you compute for this case, compute SNT matrices, they also appear to be the same as for the Fibonacci TQFT, at least up to a phase in front of T. And in fact, note that Li-Yang and Fibonacci, they they live on the same Galois orbit. So they're related by the Galois group action on the modular tensor categories. So however, this is, so Li-Yang is a bosonic TQFT, whereas this one that I wrote here, it's a fermionic one. So they're not related, but like whatever. Last week I had some discussions with Du. He suggested that maybe secretly here there's also a fermionic line, so maybe they're related by Galois conjugation as fermionic TQFT. So this is sort of the open problem for us, at least. But the story about this reduction and obtaining effective 3D Lagrangian descriptions and sort of getting rank 0 theories from the reduction of Argyros-Douglas theories, this part is, I think, understood in general, and then there are it still remains to understand the examples, and this is where I'm going to stop. Thank you. Say again. Yes, yes. Yeah. So, by the way, this is all. So this part is all in collaboration with Arash Ardehali and Dongming Gang, and Arash is, of course, um, the best expert on this, taking this high temperature limits and doing all possible analytics with them. So, and the observation is that you basically do this replacement in the index. So the p, what's usually called p in the superconformal index, you just rotate it by e to the 2 pi I. Whereas there's it's different from the more well-known notion of the second sheet that's related to black holes. So you just do this rotation. P appears in some non-integer power as an argument inside this elliptic gamma functions, and then after you take the high temperature limit. What do you do in practice? Um, lens no, no, it's not lens index. Um, yeah. There's something else. Yeah, the one you have to identify. You want to get the Zn quotient of your S3. Yeah, that's a different thing.